Let us continue our discussion on minimum DFA. Consider this language set of strings over 0, 1. Neither it has 0, 0 in it, nor it has 1, 1 in it. Which means if we read a 0, either it is the last symbol or the next symbol must be 1. After reading 1, either this may be the last symbol or after that we have to read a 0. At any point in time, consecutive zeros or consecutive ones, that's not allowed. Or you start with a 1, the next one must be a 0. Either you stop or you read the next one. Stop or read 0. So you get to see that 0101 pattern or 1010 pattern, that is all possible. And any other pattern is not allowed because they will have 00 or 11 in it. The simplest string or the base string is the following. Just 0 is valid and or just 1 is valid, and after this if it reads a 0 or after this if it reads a 1, that should be invalid. So it goes to a dead state or some dummy state. At this state you read 0, 1, you continue to stay here. So after reading a 0, one can read a 1, that's valid, so go to this state. And after this 1, you read a 0, it is still valid, go to this. Now you can continue to loop and accept 0101 pattern or 1010 pattern, and that's all allowed. Now you see that it is clearly a deterministic machine for each of them, and on input symbol 0 you get to see that it is a unique transition. On 1 it is a unique transition, similarly for each of them. Okay, and you get to see that this one has got 4 states. Let's check whether this is indeed minimum. Okay. So to start with, you group non-final states, on the other side final states. So we have a state containing Q0 D and another one containing Q1 Q2. So this is our start state, Q1 Q2, this is our final state. Let's look at the transition. Q0, 0 is Q1 and D, 0 is D. So now you see that on reading a 0, we go to more than one state. So this is clearly not a deterministic machine. So why is this happening? You see that delta of Q0, 0 is Q1 and delta of D, 0 is D. Therefore, Q and D are distinguishable. So output of this is one partition, output of this is another partition. So if it goes to two different partitions, then those two states are distinguishable, which means we need to split them. So if we split them, what will happen? We get Q0 and another state is D and followed by Q1, Q2. So let's look at this. Now these two cannot be split. Let's look at Q1, Q2. And Q1, 0 says D. Q1, 0 says D. Q2, Q2 comma 0 says Q1. So delta of Q1 comma 0 is D, delta of Q2 comma 0 is Q1, which means these two outputs are in two different blocks with respect to this partition. So therefore D and Q1 are distinguishable. Okay, and because they are distinguishable, you need to split them. So you get Q0, you get D, you get Q1, you get Q2. So this was our initial partition. Then we moved on to this partition. Then finally we get this. Now, when do you split a partition? If it has at least two states, because we are looking for a pair which is distinguishable. If exist, we split them into two. The moment you find a pair, split and go to the next level. In that again look for a pair and split if they are distinguishable. But when each block in the partition is a singleton set, no need to partition any further. So you can stop now. And what we have is precisely a minimum DFA. So this says Q0, D, Q1, Q2, and they are all different. They cannot be merged. So which means this one is precisely a minimum DFA. Remember, if you start defining zeros and ones with respect to each of them, then you precisely get this, because you get to see that each block in the partition is precisely a singleton set. So now this shows that our intuition that start with the base string and add remaining transitions, this idea seems to be working for this example as well. So one state is not possible because there are non-final states. Two state is not possible. Three state DFA is not possible. Four state, which means what we obtain or what we have drawn over here is precisely a minimum DFA. Fine. The same problem one can also approach like this. So to answer this, what we can do, let's construct the language containing a set of strings containing 0, 0 or 1, 1. Okay, and then take the complement. So complement of this language is precisely what we need. Okay. Let's try this approach and see whether are we really getting a minimum DFA through this procedure. If not, let's employ our strategy and obtain a minimum DFA. So let's construct containing 0, 0 and then take the complement. So we start here and read a 0 followed by a 0, we reach this, or we read a 1, we read a 1, we reach this. Let's assume if this is final, then we would have accepted 0, 0 or 1, 1. There are other transitions, right? At this place 0, 1, at this place 0, 1. After reading a 0, we may read a 1. So there is a possibility that we read a 1 and we read another 1 and then complete. Or after reading a 0, we may read a 0 and then read another 0 and complete this. and that's it. With respect to this 0 1 is defined, with respect to this 0 1 is defined, with respect to each of them 0 1 is defined. And this one is clearly a deterministic mission accepting set of strings containing 0 0 or 1 1. But what is this? This one corresponds to complement of this. Okay, so we need L complement. For L complement, what we do, we make this one final, this one final, this one final, fine. Then a final state will become a non-final state, so which means these two will become non-final. Okay, so complement says set of strings not containing 0 0 and not containing 1 1. So neither 0 0 nor 1 1. Okay. Now you see that epsilon is accepted by this, 0 is accepted by this, 1 is accepted by this, and then after reading a 1, 0 is allowed. If you read the next one, we go to a non-final state. Similarly, after a 0, 1 is allowed, and if you read another 0, then we go to a non-final state. Okay, so this automaton has got 5 states. So we clearly see that this one will not be minimum, because we have already proved that there exists a 4-state minimum DFA for this language. Okay, so between these two, the only difference is because we come from L to L complement, we see that epsilon is also accepted by this automaton. In this we have not included epsilon. We said base strings are 0 and 1. If you include, then even this will become the final state. Okay. So just to ensure consistency is there, what I'll do, I'll drop epsilon, and similarly I'll make this one a non-final state. Okay. So which means the set of strings accepted by this automaton starts from 0, 1 and so on. Similarly over here also it starts from, let me call this one as L1 and this one as say L2. Then it starts from 0, 1 and so on. Okay. Fine. So otherwise, yes, epsilon is allowed, because we have discussed this automaton starting from the base string as 0 and 1. So just to ensure that consistency is there, I've removed epsilon and then made this one a non-final state. Okay. Now with this framework, we see that this is not a minimum DFA, because just now we have proved that this one is minimum. So let's employ our procedure and obtain a minimum DFA for this. So as always, group non-final and final. So Q0, Q2, Q4, Q0, Q2, Q4, non-final, Q1, Q3, final. Okay. So let's check whether this is distinguishable. Q1, 0 is Q2, Q3, 0 is Q1. Delta of Q1, 0 is Q2, it's going here, and delta of Q3, 0 is Q1, which means the outputs are in two different blocks. That shows that Q1 and Q3 are distinguishable. which means split the partition, P0 becomes P1, so you get Q0, Q2, Q4, Q1 and Q3. So this is one block, this is another block, this is third block. And these two cannot be split any further. Let's focus on this. Now let's look at this. Identify a pair which is distinguishable. Okay. So let's look at say Q0. So Q0 says Q0 comma 0 is Q1. Delta of Q0 comma 0 is Q1. Okay. And then look at Q2. Delta of Q2 comma 0 is Q2 itself. So Q0 output is Q1, Q2 output is Q2, and they are in two different blocks. This implies that Q0 and Q2, they are distinguishable. So go to the next partition, in which split Q0 separately, Q2, Q4 separately, Q1 and Q3. At each iteration, we identify exactly one pair that are distinguishable and split them into two partitions. Okay. And now look at this pair and check Q2, Q4 because these three are singleton, this cannot be split any further. Now look at Q2, Q4. Q2, Q4, if you see, Q2 comma 0 is Q2, Q4 comma 0 is also Q4. Similarly for 1, which means determinism is preserved here, and whereas at these two places determinism is not. Okay, so which means stop and one state for Q0, that will be the start state, one state for Q1, one state for Q3, one state for Q2, Q4. Q0 comma 0 says Q1 and Q0 comma 1 says Q3 and Q1 comma 0 says Q2 and Q3 comma 0 says Q1. Fine. And Q1 comma 1 is Q3, Q3 comma 1 is Q4, and with respect to this 0 comma 1 is here. Now for this 0 1 is defined, for this 0 1 is defined, for this 0 1 is defined, for this also. Now Q1 and Q3 are final, so make this final state, make this final state. That's all. Now it accepts 0, it accepts 1, then after that followed by a 0 or followed by a 1. The moment you read the second 0 or second 1, you reach this dummy state. Now you see that these two states are dummy states, and in the minimum DFA they are combined into one to get an automaton like this. So now this automaton, if you apply our procedure, we get a 4-state automaton. We clearly see that 2, 3 and they are not minimum. Therefore, 4-state automaton is minimum and one cannot split this any further. So this clearly tells you that either if you follow direct construction, at times we may end up getting minimum DFA, or we employ some other technique and obtain an automaton for this language, and in case it is not minimum, follow this procedure to obtain minimum. Okay, so this tells you here is a systematic way of obtaining a minimum DFA from a given DFA, and so this kind of completes the cycle. So one can always get a minimum DFA for a given language, maybe directly or through a procedure like this. And we also see that through this procedure what we obtain is indeed minimum. Fine.